Determine how the concavity changes for the function f of x equal to 1/2 x minus psi of x on the interval 0 to 3 pi. So let's talk about concavity. Concavity, you can think of that as these two examples I have here. This one and this one. This function, the graph here, concave up. And this one concave down. And to make it easy to remember, you can think of that as, say, a parabola y equal to x squared. You can think of the other example, y equal to minus x squared. Concave up and down can be determined by the second derivative. So for example, this function, I call it f of x. F of x equal to x squared. F prime of x equal to 2x. F double prime of x equal to 2. This is positive. So next time when you forget to think about this case, concave up, the second derivative is positive. So the theorem we have is that if f double prime is positive, we have the graph, the function is concave up. And if f double prime, so let me call this f double prime in this case is equal to minus 2. If f double prime is negative, then you can tell that the graph must be concave down there. F double prime negative, concave down. And if the concavity change the sign, then you have inflection point. So note, if f double prime change size at c. For example, c is here, x equal to c. Suppose f double prime of c is 0, and before that it is positive, after that it is negative, or negative, 0, positive. Then either way, you have x equal to c is an inflection point. So that is a point where the concavity changes. Let's do this for our example here. F of x equal to this function, x on 0 to 3 pi. All we need to do is to compute the second derivative of f. F prime of x equal to 1/2 minus psi prime cosine. F double prime of x, cosine prime minus psi. So minus, we have plus psi of x. And now we need to look at x from 0 to 3 pi. So the question only asks us to consider on the interval 0 to 3 pi. Now let us look at the unit circle. 0 is here. 0 to pi, 2 pi, and 3 pi. Pi, 2 pi here, and 3 pi. 0, pi, 2 pi, 3 pi. So let me draw the table. X and f double prime of x equal to 0. Psi of x when x equals 0 is 0. Psi of x corresponds to this vertical axis here. So when x from 0 up until pi, it is positive. So from 0 to pi, it is positive. Psi of pi is 0. So it goes like this to pi. So it's all positive here. And then now we are here from pi to 2 pi. The y-axis now here, from pi to 2 pi. We are in the negative side, 2 pi. It's 0 at 2 pi and negative here. And we continue, go to 3 pi. Size again is positive. 3 pi is positive. So you see there for the function f of x, the concavities here from 0 to pi is concave up. F is concave up here, because the second derivative is positive, and then concave down. Then concave up again. So you see that at the moment where the second derivative changes the size, you have concavity change. So for example, here you have x equal to pi is an inflection point. Similarly here, from minus to plus, the concavity change. X equal to 2 pi, this is also an inflection point. So here we have two examples of inflection point. So the question asks us to determine how the concavity changes for this function on this interval. And the answer is concave up from 0 to pi, and then it changes to concave down from pi to 2 pi, and then it's concave up again from 2 pi to 3 pi. And we can draw it like this: concave up, concave down, concave up again. And here you should have an inflection point. So you can imagine that we should expect something like that: concave up, inflection point, and then we have concave down, and then we have inflection point, then concave up again. Something like that. You can check with decimals, for example, to see the exact graph, but here's how the concavity changes.